Assalamu alaikum warahmatullahi wabarakatuh. This is ELET301 Signals and Systems, and we are in chapter number 1. This is the module number 1, and we're talking about signals. In this chapter, we are going to discuss introduction to signals and systems. Then we will move to the classifications and properties, then get some examples of basic elementary signals. Then we will move to the transformations, decomposition of signals, then energy and power. We will start with an introduction about signals and systems. In this lecture, we're going to discuss signals and systems. And this is the mean, the scientific mean. How could a person describe a phenomena in our universe? So in the ancient time, people were just describing by words, and these days, once the scientific method is approach is used, we're trying to move from a word description of phenomena to a quantitative systems and signals of expressions like numbers. So it is converting into numbers. The phenomena and observations, we find a mean to convert them into numbers. So what is a signal? Is a function of independent variable, for example, it's time, that represent a physical variable of interest like voltage. So it is voltage as a function of time. So that is a signal. The function could be of one or more independent variable. For example, if we want to see a one-dimensional signal, a voltage or current in electrical circuit is a good example. Another example is recorded speech as a function of time. So when I'm talking to you right now, my voice through the mic has been recorded and has been changed into numbers, quantized into numbers. So my speech is a physical phenomena, has been converted into numbers, like the measurements as per the microphone has been able to detect. So there are two categories of signals. Either we're talking about continuous domain, time domain, or discrete time domain. So in the continuous time domain, the function is connected and defined over a period of time. For the discrete, it is a discrete point separated by some steps. So that's the difference between continuous and discrete. If we're talking about the other dimensions, like if we want to have two-dimensional signals, one example is the image brightness, and the independent variable would be the x and y coordinates. Let's see an example in the next slide. So this is an x, y coordinate at which we can describe this signal. So these are the independent variables. This is y and this is x. So based on the value of x, let's say it is 4, and the value of y, let's say it is another 4 here, so we will move to this point. And the brightness, if it is given by from 0 to 100, if it is white to black, so at this maybe the brightness of the function of x and y. So we have two independent variables describing this function f, which is the brightness. So if this equal to 4 and this equal to 4, we will get, let's say this is not too dark, let's say it is about 20 on the scale from 0 to 100. So if we decrease the y component and we move to this point, let's say this is 1, so y becomes 1, x is the same. So at this moment, now it is too dark, maybe 100%. and so on. So this is a signal given by two independent variables. For the discrete signal, this is an example. If we're talking about US wheat ending stock, so based on the year that we are looking for, it will give different values. For instance, if we're talking about the year 2001, it was about 800. And if we move to the year 2016, it will be about 1200. And that is another example of discrete signal. Then we will move to the system. And the system is a process that is applied on an input signal and transfer it to produce an output signal. So this is the process. We receive an input and then we produce an output. These two sides, what we call it signals, and the one which connect between the input and output, which we call it the system. So in this course, we are not caring much about what is inside this box. We will just represent it as a box, black box. I don't care what is it. Is it electrical? Is it mechanical? Is it social effect? Whatever. These are the systems. We are not caring about the detailed fundamentals or physical process going on. It is just a system, and we receive an input, and we're looking and observing an output. That's it. So what is inside here, we call it transfer function as per this. So h of t, so we have x of t, and it come into this transfer function h of t, then we will produce y of t. So as an example, I like this example to demonstrate the linear system. Let's erase this. So as an example, if we're talking about the system as your cart moving some stuff or some material. So if one horse is able to move 100 kilogram. So if we add two horses, we will be able to move 200 kilogram, as we can see from this figure. And this one will give you like the input will be the number of horses, and this is the system, and the output, the amount of material that, or the weight of the material that we want to carry on or transfer. So for this system, it looks very linear. So even if you add 3, you will be able to go with 300 kilogram. Similarly, if we're talking about VI relationship, like the voltage on the circuits, if we are monitoring the current while we are applying some voltage here, and the resistance, let's say it is 1 kilo ohm, so applying 10 volt at the input will produce the output 10 milliamps. Applying 20 volts will produce 20 milliamps. So again, this is a linear system. Now, if we want to talk about nonlinear system, the COVID-19 spreading is a nonlinear system. So if we are talking about in the 10th day, the number of cases, let's say 3 cases. At day number 15, the number of cases becomes 30 cases. And if you move to 20, it might reach to 10,000 cases. So this is an exponential growth, which is not linear anymore. So that is not a linear system. In fact, if we talk about systems, we have two categories: linear system and nonlinear systems. And in this course we will focus more on the linear system. From another perspective, we can categorize the systems as time varying and time invariant system. So again, in this course we will be focusing on the time invariant system. So with this, if we look for an electrical circuit with a resistive load, if you do the measurement today and we apply 10 volt, and this was 1 kilo ohm, the output, if we're monitoring the current will be 10 milliamps. If you did this experiment tomorrow, again same results will happen. If you did it in an hour later, it will be the same. After 1 year, it will be the same. So this is time invariant system. There are some systems which is changing as the timing is moving. So that will be a time varying system, which is out of the scope of this course. In this course, we are discussing the linear system, which is here, the A. So linear systems, and it has to be time invariant system, which is number 1. So these two both together is the scope of our course. So if we put both together, so this is the system here, this is the system that we're talking about, and this is the signal at the input side, and this is the signal at the output side. So this will be converted into an expression, and this will be converted again into expression, and this system will be just as a black box, and what is inside here we will be writing it as a function h of t. So that is our target in this course. Is we are not going to go through the physics behind it or through the details of what is inside the system or how the signals was measured or how did we produce or generate these values of input or output, rather than analyzing a system as it is given an equation for inputs, outputs, and systems. It could be given as like numbers, tables, or plots. Numbers, plots, or functions. So if we want to see the effect of the system on a signal, for example, if this is the input signal and we process this is the input, and we process this into a system, the output would be this. And clearly, this system is doing just taking off the high frequency part of the signals, and this is what we call low pass filter or just simply filter. Another example is for the two-dimensional. This is the input signal, and of course this is as a function f of x and y. So this is the input, and then it produced this output, which is f2 as x and y again. So this input is processed through the system and producing this output. So this system is doing some changes on colors and zooming into the picture to see some details of this picture. So this is one of the applications of this course. Again, if we're talking about systems, we could have system A, and we could have system B, and we connect them together either series, parallel, or feedback. So this will be discussed later in this course. And then whenever we're talking about system, we have to think about stability of that system also. There are many different aspects when we talk about this course. We can talk from time domain, and also we can talk about it from frequency domain. And whenever we're talking about time domain, we will come up with either continuous or discrete. And when we talk about frequency domain, we need to think about Fourier transform, Laplace transform, Z transform, as we will see in this course. To summarize, in signals, we have categorized the signals based on the types to continuous signals or discrete signals. From other perspective, as per the dimensions, we have talked about 1D, 2D, and 3D. And the focus of this course mainly will be on 1D, but you can do some projects or some additional work on 2D or 3D. And in the beginning of the course, we will focus more on continuous, and at the end of the course, we will touch on the discrete part. If we move to the systems, we will categorize based on the linearity to linear systems and nonlinear systems. And if we talk about time, we will talk about varying or invariant systems. And the focus will be again on linear invariant, time invariant system. Then if we talk about the domains, we have the time domain, frequency domain, and the time domain we have the continuous, discrete, and for frequency we have the Fourier, Laplace, and Z transform. In fact, this slide summarizes the picture of the entire course. This is an example of describing the concept of interaction between the signals and systems in our daily example. And just this is to visualize the concepts based on these examples given here in this slide. Let's say that the signal can be represented as a student. It is a human, so this guy here just smiling for us. And the system is a school, which the student enters as a fresh student going into the preparation year, and at the end it is graduated from the school. So this is the student, and we can plot different behaviors of the student and generate these data into a plot. So this student can be represented by the signal. We can represent it from age perspective. We can represent it by the grade that he's approaching, the time that he's working. I mean, there are different ways how we categorize even the weight, like some characteristics. Even we can take the picture of the students and analyze these as an input signals. Once this student entered the school, it has to deal with this system somehow. And at the end of the day, the student will get graduated. So this guy becomes this guy. So again, we have to find a way to get the data from the students to represent as an output. So here, if the age was certain numbers, then it will change to a certain number because it is entered through the systems. And if this was like the grade that he is approaching the first semester, this is the grade at the last semester, or so on. So it is a characteristics associated, certain characteristics associated with this students. We can look at it from different perspectives, from time domain, from frequency domain, like how many times he's eating per day, or how many times he's studying, eating, whatever, how many times he's going to the school, how many times he's opening, reading, whatever. So from frequency response or from frequency domain, or we can do it from time domain, how much time he spent till he finished subject, reading a subject, certain subject, before entering the school and after entering the school, and see what is the system effect on this signal. In fact, we can analyze these things from a continuous perspective or discrete perspective, and we can look at it from 1D or 2D like pictures, or 3D like body weight and so on, or body structure and so on. And for the system, we can look at it from linear, whether the effect of this school on this student before and after. If we use Ahmed as an example, and he scored like A's compared to Badr, and he scored B's or C's. And then after the school, Ahmed becomes A again, and Badr becomes again A. So there was an effect on these students results through this good school. But if it was bad school, maybe Ahmed will not get an A anymore. He will get maybe B, and Badr will not get B anymore. He will get C. So that's a bad effect on the from the school on the students. So those are the examples of these things on real life. I try to just demonstrate it for you to help understanding this concept. Thank you for listening, and see you in the next lecture.